In this session and the next couple of sessions, our learning objectives are as follows. We will talk about solutions. That's our focus. We will talk about some definitions, common terms that are used in context of solutions. But more importantly, we will spend time in calculating solution concentration, and the only concentration unit that we will deal with or work with rather is molarity. Your textbook may have several other units of concentrations that are discussed. Please only focus on molarity. The others may be dealt with later on in your future chemistry classes. But for now, molarity is our only focus. We will definitely talk about dilution and also some stoichiometry with solutions instead of using pure substances. Okay, so let's get started with definitions. What is a solution? A solution is a homogeneous mixture of two or more pure substances in such a way that it's a physical combination such that all the components of that homogeneous mixture retain their chemical identity. We've discussed this in a previous session a few chapters ago, where we talked about classification of matter, how matter can be pure substances and mixtures, what makes a pure substance pure, blah, blah, blah. We also talked about how mixtures can be homogeneous, heterogeneous. So please go back to that session to review that material to remind yourself of the definitions. But a solution is a homogeneous mixture of two or more pure substances such that all the substances, all the components retain their chemical properties. So let's think of some examples. Please go ahead. Let's brainstorm a little bit and think of some examples. You go ahead and I will do that too. Tap water is not pure water. It has water dissolving several substances in there, so that's really a solution. Soda is a solution too, as long as of course you don't see the carbonation, as long as you don't see the fizz, it's a solution. Brewed tea and brewed coffee, those are teas or coffee, those are solutions as well. Air is a solution. Air on a clear day when you do not see fog, you don't see moisture, it's a homogeneous mixture of several components. Blood, as long as it's not coagulated, as long as it hasn't solidified, it is a solution. Juice is a solution. What about sterling silver? Is it pure silver? How about steel? How about bronze? Those are not pure substances. Those are what we call metal alloys, and those are homogeneous solutions too. Solutions can be liquid solutions, they can be gaseous solutions, or they can be solid solutions as well. All solutions have two parts to them. They all have a solute and solvent. A solute is defined as the component in the mixture that is dissolved. The more correct definition of a solute is the component in the mixture that is present in relatively smaller quantities. There are often times that you can't say what substance is dissolved which is the substance that is dissolving. I mean, just because salt dissolves in water, does it mean that water always has to be the solvent and salt always has to be the solute? The answer is no. It really depends upon the relative quantities of the two components. So the solute is the component in the mixture that is present in relatively smaller quantities compared to the other component. And solutes can be solids, liquids, or gases. There is no rule that says that there's only one particular physical state that the solute must be in. So here are some examples of solutions where hopefully you'll notice that the solutes are in different physical states. Brewed coffee, caffeine is a solid. If you added sugar to that coffee, sugar in its pure form is also a solid. Sugar water, of course, sugar is a solid. Vinegar is not a pure substance. It's a homogeneous mixture, a solution of something called acetic acid in water. Acetic acid in its pure form is a liquid. Nail polish remover, acetone, the solute, is a liquid in its pure form. Air, oxygen, and other gaseous components in air that are solutes are gases in a pure form. Soda, carbon dioxide that is dissolved in soda, is also a gas in its stable form. Sterling silver has silver mixed in with small quantities of copper, and therefore copper is the solute and copper is a solid at room temperature. So there is no restriction as to what physical state a solute can be in. Solvent is defined typically as a substance that does the dissolving, but once again, as I said before, the more accurate definition of solute and solvent are based on relative quantities. The component in the mixture that is present in relatively largest amount is called the solvent. And solvents can also be solids, liquids, or gases. And here are some examples of solutions, once again, where the solvent happens to be in different physical states. Brewed coffee, tea, water is a solvent, that's a liquid. Dental filling uses a mixture where silver is the solvent. It's the major component amount wise, and it's a solid at under normal conditions. Air, nitrogen is the biggest component in air, and that's a gas at room temperature, room pressure under normal conditions. Water is a liquid, that's a solvent in soda. Sterling silver, silver is the solvent because that's the major component, and silver is a solid at room temperature. So once again, just as solutes, solvents can also be in any physical state of matter. Okay, so there are some other terms that are relevant in relation to solutions. One of them is solubility. Solubility is defined as the maximum amount of solute that can be dissolved in a given amount of the solvent at a given temperature. So it's the maximum amount of solute that can be dissolved in a certain amount of the solvent at a certain temperature. Solubility is highly temperature dependent. If you change the temperature, the amount of solute that can dissolve in that same amount of solvent will change. Okay, so here's an example of how solubilities are often listed in data banks that have physical data listed. So for example, for salt, 37 grams of salt can be dissolved in 100 grams of water at 50 degrees Celsius. So that's how generally it is listed. In other words, if you have a solution that contains the 37 grams per 100 grams of water at that temperature, then we've created a saturated solution. A saturated solution already has the maximum quantity of solute dissolved in the given amount of solvent at that given temperature. Whereas unsaturated solution still has room to dissolve more solute in that given amount of solvent at that given temperature. It has less than the maximum quantity of solute dissolved in the given amount of solvent. For example, using the same value of solubility for salt, here is an example. So if you have 37 grams of salt dissolved in 100 grams of water at 50 degrees Celsius, you would have a saturated solution. What if we had 27 grams of salt dissolved in 100 grams of water at 50 degrees Celsius? The solution is unsaturated. It still has room for 10 more grams of salt. So here are some basic idea amounts given at different temperatures for you to try and be able to figure out the difference between the terms saturated and unsaturated. Please remember, terms saturated and unsaturated are based on solubility of that solute in that given amount of the solvent at a specific temperature. There are a couple of other terms that are used quite often. Those are concentrated solution and dilute solution. A concentrated solution is a solution that contains greater amount of solute in the same quantity of the solvent than another solution. So really we are comparing two solutions to each other when we are using these terms. Similarly, a dilute solution is a solution that contains smaller quantity of solute in the same quantity of solvent compared to another solution. So it's very important to understand the terms concentrated and dilute are relative to each other. They have nothing to do with the solubility of a solute in a solvent at a temperature. Basically, when you call a solution concentrated, you're comparing it to another solution, and the same thing goes for diluted as well.